In this lecture, I want to introduce another rule that allows us to manipulate sentences involving the universal quantifier. This rule is referred to by your textbook as the rule of universal introduction. It is also sometimes referred to as the rule of universal generalization. But in this class, we'll use the term universal introduction. Okay, the rule of universal introduction is a little difficult to get a grasp on, so I want to warm up to it a bit. I want to talk about a situation in which we use a similar form of reasoning. So suppose I want to prove something in geometry about all triangles. One way I could do that would be by picking an arbitrary example of a triangle, making no special assumptions about it, and proving that what I want to show holds of that triangle. So I may draw a triangle on a piece of paper to refer to, and I may start referring to that triangle in my proof, but however I drew the triangle, of course the triangle I drew is going to have specific properties that other triangles don't have. But however I drew it, I'm going to try my best to refrain from referring to any properties that that triangle has that other triangles don't have. Now, if in fact in my proof I do make no special assumptions about the triangle I picked, as I don't assume it's a right triangle or an acute triangle or anything of the sort, even if the triangle I drew was an acute triangle, I don't assume that it was an acute triangle in my reasoning. If I in fact do that and I manage to prove something about that triangle without making any special assumptions about it, then I can conclude that what I proved holds for all triangles. Well, why is that? Because I proved that what I want to show holds for that triangle. I made no special assumptions about that triangle, so I could run through the same proof for any given triangle. So if I do in fact succeed in such a proof, I can conclude that what I want to prove holds for all triangles. I'm sure that all of you have done proofs like this in geometry. A proof like this is sometimes called proof by way of generalization from the arbitrary case. And what the universal introduction rule is it's basically a rule that lets us carry out proof by way of generalization from the arbitrary case in our system. Okay, but in order to do that, we have to have some way of referring to an arbitrary case in our proofs. And so we're going to introduce a new kind of symbol into our language that allows us to do that. So far, among the new symbols that we've introduced, we have predicate letters like F, G, H, these capital letters. We have names for specific individuals that come from the latter half of the alphabet like M, N, S, and so on. And then we have variables like X, Y, and Z. Well, now we're going to introduce a new stock of symbols. These come from the former half of the alphabet, A, B, C, and so on. And we'll call these arbitrary names. Now, arbitrary names act just like names do. For example, the sentence FA reads as A is F. But instead of taking these to be names of particular individuals, we take them to be names of arbitrarily selected individuals in our universe of discourse. It's as if we had said, pick something in the universe of discourse at random and call it A. Then pick something else pick something else, maybe the same thing, pick something at random again and call it B, etc., without ever actually paying attention to just which objects we were picking out. These are arbitrary names. They might as well name any individual in our system. Okay, now that we have this device in our language, we are in a position to state the rule of universal introduction. The rule may be stated like this. If one has a line with a sentence that contains an arbitrary name, and that line depends on no assumptions that involve that name, one may infer another line that is exactly like this line, except that all occurrences of that arbitrary name have been replaced by a variable, and a universal quantifier that ranges over that variable has been placed out front. Okay, like many of our rules, the statement of this rule is quite a mouthful, but it is easier to grasp when one sees it applied. So let's look at an example. So here we have this sequent. Everything that's F is G. Everything that's G is H. Therefore, everything that's F is H. I think a moment's reflection reveals that this is in fact a valid argument pattern, and we now have the resources to prove that it is. And here is how we're going to do that. We want to try to prove a universal generalization. When one wants to try to prove a universal generalization, the way to do it is by way of the rule of universal introduction. And the way to prove something by way of the rule of universal introduction is to prove that that thing holds for an arbitrary case. So since we want to prove that for any x, if x is F, then x is H, what we're going to do is we're going to prove that for some arbitrary case, A, if A is F, then A is H. So this is our strategy. Let's go ahead and see it applied. So we begin, of course, by writing down our premises. Now we're trying to prove if FA, then HA. And we've got these premises here, but they're pretty useless to us in their current form, but they'd be useful for proving things about A if we had, or we would have something useful for proving things about A if we had lines that had A in them. So I'm going to go ahead and apply the rule of universal elimination to line 1 to get if FA then GA. And I'm going to do the same thing to line 2 to get if GA then HA. Okay, now I back up and I consider what my goal is. My goal is to prove a conditional. Right now my goal is to prove if FA then HA. Now we go back to what we did before. We go back to all the things we learned when we did propositional logic. We're trying to prove a conditional. Our rules of thumb for proving conditionals tell us that we ought to assume the antecedent and then try to get the consequent. So I'm going to assume FA on line 5 and make it my goal to get HA. Well, I note now that I have FA on line 5, one thing I can do that might advance me closer to my goal of proving HA is I can go ahead and apply modus ponens to lines 3 and 5 in order to get GA on line 6. So I've done that. And yes, now that I have GA on line 6, I can apply modus ponens to lines 4 and 6 to get HA. Now I've achieved one of my subsidiary goals, which was to get HA. So now I back up and consider what my previous goal was. My previous goal was to get the conditional if FA then HA. So I can get that by discharging the assumption that I made on line 5 by applying conditional proof to lines 5 and 7. Okay, now I'm almost done. I have this conditional if FA then HA. What I want to prove is that for any x, if fx then hx. So it looks like I can do that by applying the rule of universal introduction. One thing I need to check though is I need to look at line 8 and make sure that line 8 doesn't depend on any assumptions that have A in them. Make sure that line 8 doesn't depend on any assumptions that have the arbitrary name A in them. Well, in this case, that condition is met because line 8 depends on no assumptions whatsoever. So since line 8 depends on no assumptions whatsoever, it meets that condition. I can apply the rule of universal introduction. So I'm going to go ahead and do that. I apply the rule of universal introduction to line 8. And what I do is I put a universal quantifier out front that ranges over the variable x. And I replace each occurrence of A in line 8 with the variable x. And now I have completed my proof. So this is one example concerning how to apply the rule of universal introduction. Let's go ahead and look at another one. So here we have the sequent, everything that's f is g. Therefore, if everything is f, then everything is g. I think that reflection shows us that this sequent is also valid, and we can prove that it is. So we begin by writing down our premises. Now our goal right now is to prove a conditional. And right now, since my goal is to prove a conditional, I don't really need to think very hard about what to do next. I just need to consult my rules of thumb. My rules of thumb tell me that when I want to prove a conditional, what I do is assume the antecedent and try to get the consequent. So I assume everything is f on line 2 and make it my new goal to derive everything is g. Okay, so now I want to derive everything is g. That is, I want to derive a universal generalization. My rule for proving universal generalizations is that I will try to prove that the generalization holds for the arbitrary case. So since I want to prove that everything is g, what I'll do is I'll try to prove that some arbitrary thing is g. That is, I'll try to prove that a is g. So my new goal right now is to prove GA. Okay, so I've got these universal generalizations on lines 1 and 2. My goal is to prove GA. These universal generalizations as they currently are pretty useless when it comes to moving me closer to that goal. So I'm going to write down lines that are more useful to me by applying the rule of universal elimination to lines 1 and 2. So I apply it to line 1 to get if FA then GA, and I apply it to line 2 to get FA. Okay, now that I've got lines 3 and 4, I see that I'm in a position to apply modus ponens to get GA, which was one of my subsidiary goals. So now I back up and consider what my previous goal was. My previous goal was to derive the universal generalization for any x, gx. And I'm in a position to do that given that I have GA on line 5, provided that line 5 doesn't depend on any assumptions that contain the arbitrary name A. Now line 5 does depend on an assumption. It depends on an assumption made on line 2. So what I need to do is I need to look back at line 2 and see if what occurs on that line contains the arbitrary name A. So I look up there and I see that in fact A does not occur on line 2. So I am in a position to apply the rule of universal introduction to line 5. So I'll go ahead and do that. So now I have everything is G. Okay, now I've accomplished another one of my subsidiary goals. So I back up to my previous goal. My previous goal was my main goal, which is to get the conditional that I'm trying to prove. And I can get that conditional by discharging the assumption that I made on line 2, by applying conditional proof to lines 2 and 6. And I have now completed this problem. Okay, I've given you a homework assignment that allows you to practice using the rule of universal introduction. So go ahead and do that, and then I will see you again later on.